Hey everyone, and welcome to This Explainer. Today we're going to explore the absolutely fascinating world of grade 8 geometry by using dynamic geometry software to construct and transform figures. If you've ever wondered how digital tools can act as a kind of mathematical sandbox, giving us the power to visualize, stress test, and really understand how shapes behave when we move them around a coordinate plane, well, you're in exactly the right place. We are going to bring these foundational geometry concepts to life right before your eyes.
Okay, let's dive into this. Here's the 6-step investigation we're walking through today. 1. Constructing with geometry software. 2. Exploring rigid transformations. 3. Pause check, invariant measurements. 4. Testing conjectures by dragging. 5. Pause check, patterns versus proof. And finally, 6. Recap and transfer question. Let's get right into it. Section 1. Constructing with geometry software. So before we can actually transform a shape, we've got to build one, right? Think of digital geometry platforms, like GeoGebra for instance, as your ultimate mathematical sandbox. Instead of furiously erasing mistakes until you literally tear a hole straight through your graph paper, you get to use precision digital tools to build geometric figures step by step. First up, you grab the point tool. Now a point is just a location, but when you drop a few of them down, they become the vertices of your future shape. Next, you use the segment tool. Our geometry standards tell us a line segment connects 2 points, so you just click your points to link them up. And finally, the polygon tool. By connecting a series of points and coming all the way back to your starting vertex, you create a fully closed two-dimensional shape. And just like that, the whole shebang is constructed and ready for our next steps.
Moving right along to Section 2, exploring rigid transformations.
Now that we've got our polygons sitting perfectly on the coordinate plane, we have to ask the obvious question. What happens when we want to move it? In geometry, we call these movements rigid motions, and the software lets us execute them flawlessly. There are 3 main types you absolutely need to know. First is a translation. This is simply sliding the figure along a path, up, down, left, right, or diagonal, without changing its orientation at all. Second is a reflection. Imagine dropping a mirror right onto your shape. A reflection flips the figure across a specific line, creating a perfect mirror image. Third is a rotation. This means turning the figure around a specific center point by an exact angle, like 90 degrees or maybe 180 degrees. Using the software, you can apply these transformations with a single click, shifting your constructed polygon right across the plane.
Which brings us to Section 3, pause check, invariant measurements. All right, it is time to test your understanding of what's actually happening mathematically behind the scenes during these rigid transformations. Here is the question. When we translate, reflect, or rotate a figure on the coordinate plane, which specific geometric measurements remain exactly the same? I want you to literally pause and think about this for a second. If I slide a triangle across the coordinate plane, what properties of that triangle absolutely refuse to change? Well, if you guess the overall size and shape, you hit the nail on the head. Based on grade 8 geometry standards, rigid motions preserve very specific invariant properties. And invariant simply means they absolutely do not vary. Under any translation, reflection, or rotation, lines are taken to lines. Line segments remain the exact same length, so if a side was 5 units long before sliding, it's going to be 5 units long after. Angles maintain the exact same measure, and if your original shape had parallel lines, those lines remain parallel after the transformation, for sure. The software perfectly preserves all these measurements, keeping your shapes congruent.
All right, Section 4, testing conjectures by dragging.
This is where dynamic geometry software totally separates itself from traditional paper and pencil. We aren't just looking at static pictures anymore. We're working with living, breathing mathematical models. And this brilliantly illustrates one of the core standards for mathematical practice, specifically practice number 5. Use appropriate tools strategically. Proficient students know that dynamic geometry software is basically the absolute best tool for visualizing the results of varying assumptions. It lets us explore consequences and deepen our understanding in ways that just drawing a single triangle on a piece of paper simply cannot do. But to use this tool strategically, we first need to make a conjecture. In mathematics, a conjecture is essentially a really educated guess. It's a conclusion or a proposition based on experimental observation that still needs to be rigorously tested. You might look at a transformed shape and think to yourself, I bet these 2 opposite angles are always equal. That right there is your conjecture. But how do we act like real mathematicians and actually test it?
We do it using the drag test. Honestly, this is the real magic of dynamic software. Here's how it works. Step 1. Form your conjecture about a transformed shape.
Step 2. Select the Move tool, which is usually just the little cursor arrow in your software's toolbar. Step 3. Click and drag a vertex of the original figure. You stretch it, pull it, warp it, whatever you want. And step 4. Just observe. As you drag the original vertex, the transformed shape automatically updates in real time. If your conjecture is true, the corresponding measurements, like those angles or parallel lines, will maintain their mathematical relationship no matter how wildly you drag that point. You are literally stress testing your math on the fly.
Section 5, our second pause check. Patterns versus proof.
Okay, so we've seen how powerful the drag test is, but we also need to understand the absolute limits of the technology we're playing with. Let's say you drag a vertex around for 5 solid minutes, and that angle relationship you conjectured holds up every single time. Does seeing this consistent pattern on your screen mean you have formally, mathematically proven it to be true?
Now, what's really interesting about this slide is the answer is a definitive no. A dynamic diagram on your computer screen only suggests mathematical patterns. It allows you to experimentally test conjectures, but software is definitely not a replacement for a formal proof. In geometry, a formal proof constructs viable, logical arguments using definitions and axioms that mathematically guarantee a statement is true across all infinite possible cases, not just the ones your screen rendered during those 5 minutes. The software is an incredible discovery tool, but the logical proof, that is what actually sets the math in stone.
And finally, Section 6, recap and transfer question.
Awesome work today, everyone. Let's head into a quick recap. So the crucial point is this. Geometry software lets us construct precise figures using points and segments. Once they're built, rigid transformations like translations, reflections, and rotations move those figures across the plane while keeping their core measurements entirely invariant, meaning lengths and angles do not change. We can use that awesome drag tool to stress test our conjectures dynamically, but we have to always remember that seeing a pattern on a screen doesn't replace the rigorous logic of a formal geometric proof. I want to leave you with a final thought to ponder. If you use software to reflect a polygon across a line, and then you grab one of the original vertices with a Move tool and drag it upward, how exactly will the corresponding vertex on the reflected polygon behave? Will it go up, down, or just stay put? I highly encourage you to go open up a digital geometry sandbox, construct a shape, and find out for yourself. Thanks so much for joining me on this explainer, and hey, happy experimenting.